In our last video, we talked about type 1 and type 2 errors. That is, we took the true state of the world, where the null hypothesis may be true or the null hypothesis may be false. Once again, think about that as being X is innocent or X is guilty. And we combine that with two possible decisions, where we think about rejecting the null hypothesis or we think about failing to reject the null hypothesis. Once again, we can conclude sort of intuitively that the X variable is guilty of Y. That would be rejecting the null hypothesis. So if we reject your innocence or reject the null relationship, we think you're guilty. Or our alternative decision is we can fail to reject the null hypothesis. In other words, we think you're innocent based on the evidence. And that, of course, created our 2x2 table where we can possibly make an error, type 1 error, which is concluding that a relationship exists when one in fact does not exist. That is, we reject the null hypothesis when the null hypothesis is true. Or a type 2 error where we fail to reject the null hypothesis when the null hypothesis is in fact false. In other words, we think that a relationship does not exist when one in fact or in reality does exist. Now, the follow-up part of this, thinking about type 1 and type 2 errors, is that if we're going to be making decisions that could lead to errors, at what point are we comfortable with making those decisions? Once again, this is true both for court or legal proceedings, and this is also true for statistical analyses, given that type 1 errors and type 2 errors are always possibilities. As we mentioned in the last video, though, type 1 errors are the more egregious error, the more error we're concerned about making, because they are harder to resolve once those decisions have been made. Once again, in court, the analogy is we're more concerned about protecting an innocent person from being wrongly convicted and sent to prison than perhaps setting a guilty person free. So once again, type 1 errors are always kind of viewed as being a little bit worse than type 2 errors. Which begs the question, at what point are we comfortable making a type 1 error? At what point are we comfortable convicting an innocent person or innocent suspect? So when you think about this in legal proceedings, in kind of every court show that you see on TV, the standard of judgment by which we would convict a suspect, that we would feel comfortable perhaps as a jury, maybe sentencing a person to prison, even if they are in fact innocent, is when the evidence that is presented is beyond a reasonable doubt. If you've ever been to student conduct board at a university, the same proceedings happen where we're trying to figure out if students have committed some violation of the code of conduct. The standard's a little bit different, though, in student government, where the standard is beyond preponderance of evidence. Okay, so in court, we think we can sentence people for crimes when we have sufficient evidence to be beyond a reasonable doubt. And thinking at sort of lower stakes, student government or student judiciary committee, preponderance of evidence is the standard. Now, while we use that language to talk about when we're comfortable making a type 1 error, that is, when we're comfortable convicting, we don't think about that in perhaps numeric terms. So I often challenge students to think about, well, what would be the percentage of confidence you would have to be beyond a reasonable doubt? Would you want to be 99% confident? Would you want to be 99.5% confident? Would you want to be 99.9% confident? Would you only want to be 80% confident to say this person's guilty and is going to go to prison to satisfy the beyond a reasonable doubt kind of language or kind of framework? Preponderance of evidence, most people take to mean that it's more likely than not that you were responsible for violating the code of conduct. So we might say that as long as you're over 50% confident, maybe 50% plus 1, 51%, or maybe 50.5%, we would say that we have satisfied the preponderance of evidence threshold by which we're willing to say you are responsible for that violation. So the way to think about what we call statistical significance is simply a threshold by which we are willing to accept a type 1 error. So kind of drawing that analogy back to our standard of beyond a reasonable doubt and our standard of preponderance of evidence, there are just two different lines we can draw on that 0 to 100 probability spectrum or confidence spectrum to say we are accepting a type 1 error. Once again, if you think about where we are, that midpoint for preponderance of evidence, we would want to say we want to be a little bit more than 50% sure that you were responsible for committing the violation of the code of conduct. Whereas if we're looking at, let's say, you going to prison for a long time, we want a much higher threshold, beyond a reasonable doubt. How much doubt are we willing to accept? What is reasonable doubt? Is it 5% doubt? Is it 10% doubt? Is it 20% doubt? Right? Those are different frameworks we can think about, even though we normally don't put a numeric value to it. So statistical significance is simply the language we use in statistical inference to define that threshold. So you can think about preponderance of evidence, you can think about beyond a reasonable doubt, and then there's going to be another line drawn somewhere on that confidence spectrum of 0 to 100 that defines statistical significance. Now in social science, we define statistical significance most commonly as 95%. That is, we're saying that if we're going to conclude that a relationship exists between X and Y, we want to be 95% confident the null hypothesis is incorrect. Or alternatively, the way we can frame that is for statistical significance, we want to be confident that the null hypothesis is true at 5% or less. If we're 95% confident the null hypothesis is incorrect, that means we are using our probability rules of subtraction. We're knowing then that we have a 5% chance or less that the null hypothesis is true. So at that point, when we achieve that 95% confidence, or 5% likelihood the null hypothesis is true, we would declare the relationship exists, keeping in mind that there's still a 5% chance we've made a type 1 error. Let's take a quick look at the notation, which should help reinforce how those lines define these different standards of judgment for both statistical significance, preponderance of evidence, and what we might call beyond a reasonable doubt.
All right, so let's take a look at how some of this statistical significance would look in sort of a visual diagram. So recall from our discussion on probability theory that the probability of an event A of occurring has to be between 0 and 1.0, or conversely, the probability of an event A happening has to be between 0% and 100%. In other words, the probability of an event happening cannot be less than 0% or greater than 100%. Or if we do it as a decimal, it can't be less than 0.0 or greater than 1.0. If we're substituting in the probability that the null hypothesis is true for our event A, then it follows that the probability the null hypothesis is true must also be greater than or equal to 0.0 or less than or equal to 1.0. Using our rule of subtraction from probability theory, we also know that the probability of not having event A is equal to 1 minus the probability of having event A. Once again, substituting in the null hypothesis being true for our event A, it follows that the probability of not having the null hypothesis be true, or the null hypothesis being false, is equal to 1 minus the probability that the null hypothesis is true. In other words, the probability the null hypothesis is false equals 1 minus the probability the hypothesis is true, because those are the only two hypotheses we have in our set of options for the null hypothesis. Here you can see the probability of the null hypothesis being true represented on the top line graph. The probability that the null hypothesis is true starts at 0 on the left and ends with 1.0 on the right. Conversely, the probability that the null hypothesis is false, represented as the probability of not having the null hypothesis be true, is represented on the bottom line graph. Here the line graph starts at 1.0 on the left and 0 on the right. The reason I've illustrated the line graphs in this fashion is to demonstrate that the probability of H0 is equal to 1 minus the probability of not H0. Similarly, the probability of not H0 is equal to 1 minus the probability of H0, as we see in our rule of subtraction. For example, if the probability of the null hypothesis being true is 0.8, then the equivalent position on the probability of the null hypothesis not being true on the bottom line graph is 0.2. In other words, when you add the probabilities from both line graphs, you should get 1.0. Now that we have our line graphs established, let's look at our standards of judgment. Here I've illustrated preponderance of evidence with the blue line. Recall that a preponderance of evidence means that we are slightly more than 50%, or 0.5, confident that the null hypothesis is false. You'll see here this is illustrated on the top line graph, where the probability of the null hypothesis being true is slightly less than 50%. Now remember, since on the bottom line graph the probabilities run the other direction, that is, the probability runs from right to left, we can see that the same position, that the probability of the null hypothesis being false, is slightly greater than 0.5% since it's on the 0.5 to 1.0 side. Let's compare that to our second standard of judgment, beyond a reasonable doubt. Now, we haven't really defined beyond a reasonable doubt, so let's assume for argument's sake that it's maybe perhaps around 85%. Here I've drawn a second blue line to represent beyond a reasonable doubt. That is to say that we are 80% confident the null hypothesis is false, means that we're going to say that there's only a 15% chance the null hypothesis is true. So see here that beyond a reasonable doubt runs through the top line graph about 0.15. That means we are about 15% confident that the null hypothesis is true. That also means, because of the rule of subtraction, that we are 85%, 0.85, confident that the null hypothesis is false, which is represented on the bottom line graph. Statistical significance in social science, or any science really, is just another standard judgment on this probability of the null hypothesis being true and the probability of null hypothesis being false line graphs. Once again, we said that statistical significance in social science is often defined as the 95% confidence level. In other words, we want to be 95% confident that the null hypothesis is false, which means we're about 5% or less confident that the null hypothesis is true. This is illustrated in the red line on our line graphs. Here you can see that statistical significance in social science cuts the probability that the null hypothesis is true at about 0.5%, and it cuts the probability that the null hypothesis is false at the 0.95% level. In other words, to say that we are statistically significant is simply to say that we are 95% confident the null hypothesis is false, or conversely, only 5% confident that the null hypothesis is true. We can write all of these three standards of judgment as probability statements. So we can formalize that the preponderance of evidence says that the probability the null hypothesis is true is less than or equal to 0.5, or 50%, or conversely, we can say that a preponderance of evidence means the probability the null hypothesis is false is greater than or equal to 0.5, greater than or equal to 50%. Using a standard judgment of, let's say, 80% for reasonable doubt, the probability the null hypothesis is true will then be less than or equal to 0.2, 20%, or conversely, the probability the null hypothesis is false will be greater than or equal to 0.8 or 80%. Finally, for statistical significance, we're saying that the probability the null hypothesis is true is going to be less than or equal to 0.05, that is 5%, or conversely, the probability of the null hypothesis not being true is greater than or equal to 0.95 or 95%. So we can finally conclude that the confidence level is simply the probability the null hypothesis is false, or the null hypothesis is not true. So once again, a 95% confidence level also means that the probability that the null hypothesis is true is less than or equal to 0.05 or less than or equal to 5%. I know that some of this is very confusing for students that have seen it for the first time, so once again, watch the video a few times and let me know if you have questions.